Well, not through bisection, no.
Which is what the usual swinging of the arc means. You just swing an arc, put it on another point, swing another arc, they bisect, then you create a line or whatever. But you shouldn't actually have to, and you can just put where they intersect and then keep swinging. And,
well,
so basically through the process
if you
of
draw
bisection,
if you draw a circle and were to just construct its diameter, and on one point of one end of that diameter, we're to construct a circle whose circumference, or whose radius, pardon me, is equal to the radius of that circle. Okay, it will cut the circle in two places. This second circle, and now if you take either of those points, okay, and now construct the same circle again. You see, it's the same radius. It will actually cut through the point you used to draw the center of the one circle already on there. And lo and behold, you've got enough points that are equidistant from one another to take three of them, such that their distance to the center of the circle is equal, and their distance between each other is equal, the 3 points, and you have an equilateral triangle. So you've constructed a three-sided polygon.
I've done that. And the point is that...
But you can't go to 9 now.
Which is kind of contradictory, because if you can do 3, you'd figure you could just, whatever it takes, do 3 times and you got 9.
Yeah, no one's been able to do it.
Well, actually, I think you've come fairly close. Closer than anyone I've heard of, but
the problem is that what I've done is when I ask myself, okay, what have I done? And I observe it in terms of mathematical axioms. It turns out that it's not exact. I haven't really done it. It's like, in terms of mathematics that we know of, my method will produce an angle of 39.9898 and then some numbers. So it's that close to 40 degrees, but
but it's not. It's almost 9898, which is would be rounded off to 99.
Whereas I can construct a 60-degree one that's 60, exactly 90. 180, all these things. But I can't do. You can't do 40. You can't do 20.
You can't do 20?
No, you can't. You can't do 20. Like you can do 80. 80 can be done. And that, like some of these triangles.
So it's basically the property of bisecting a circle that disallows you from doing that. It'll allow you certain kinds of even-shaped polygons, to be drawn, but not certain odd ones.
One of the things I discovered.
It's interesting.
Yeah, one of the things I observed.
But only to a certain magnitude, because let's say 15 can be done. It's odd, but it's not. 13 can't be. 11 can't be, and 9 can't be, and 7
one of
can't
the things
be. So there's 4, but above it, you said 17 is doable?
Yes, possible.
Is 19 doable?
I don't think 19 is. I can't.
So there's a kind of a resonance.
There's a list of them. You can actually go on the internet and type in through a search on the internet. You can actually, there is a website that actually has a list of all polygons that are constructible and all that aren't.
Do you know what the name of that is, or no? Not today, huh?
It's interesting.
Just type in knowable polygons or drawable polygons.
Constructible polygons.
Yeah.
And you'll probably within that page of, because there's not too much you should come up with, but within that page of links, you should have one there that will actually list the number or list them all and stuff like that. Of course, I mean, when I say all, not really. I mean, it'll go to a certain range and the numbers get so large they don't bother.
So we've just been
for instance, there's I think a 200 and I can't remember some sided polygon that's been constructed, and there's a proof for it. But I mean,
but who would want to know in the first place?
Well, because the thing is,
unless you were actually using that in some sort of possibly, it could be used. I could understand when I said that laughingly. I guess there could be an application for it.
Well, the thing is, I could come up with a number, like somebody's come up and somebody has constructed one for 250 some odd sides or something like that. Or I can't remember what it is. It's something like that. But I mean, to take a larger number like 842, all you got to do is break it down in its primes to Fermat primes, and if it comes out that it can be expressed as Fermat primes 2 to the base 2 to the,
then you know you
then
can
you know you
construct
can
it.
construct it. Now, do you want to go and try and do that? Because that construction could take you 30 years or something.
Well,
and then immediately you'd probably be able to access a proof because you could just do it using the general known axioms. The thing is, no one can even do a 9-sided. Like a 9-sided can't be done. So you don't have to go off to these ones that can or can't be. Here's 9-sided figure.
Well, maybe there's maybe the thing is like much of science and technology stays away from things it doesn't understand, So they go to where it actually works and they leave alone what doesn't. And so maybe at the nanotechnology level, maybe those kinds of geometrical configurations might be necessary.
Well, the thing is, when I start drawing it,
in doing certain kinds of, I wouldn't know how I'd express that.
See, one of the things about this
how an electrical impulse would bounce around a particular chip or something. I mean, if you could construct a chip that looked, how many sides? 200 and what?
Well,
200.
It's quite between 200 and 300. I can't remember the number, but it's
it's
quite large. And
so if you had that kind of bouncing,
I think it's considered a kind of a mathematical joke that somebody went to that effort to do it. But nonetheless,
and they did it, apparently.
Some people go to play
video
machines or slot machines, and some people sit around drawing polygons.
Exactly. Well, the thing is that maybe the fact that it has been proven to be doable may at some point create a necessity for making that application. So in the
I'm not
so-called
sure.
physical world,
I think there's a way you can get lost
on the world.
There's a way of getting lost. When I say lost in mathematics, it's like where it becomes very, very complex and it's not necessary. Like, for instance, if you're drawing a geometrical figure, and it turns out to begin with, you always start off with a basic circle or something. You can go anywhere else you want, but if you stay within that circle and draw your polygons, you realize that the 9-sided polygon is there somewhere. You just can't see it. Like, so what are you doing that's preventing you from seeing it? Well, one of the things I noticed was that in my approximating it, that it was I was basing the solution on the number 1 and 3 and some of the permutations of that. Like, basically, if you the square root of 3, like if you start with 1 in terms of your radius, your equilateral triangle in that circle with that radius of 1 is each side is a square root of 3.
Okay.
So when you bisect any one of those sides by drawing a line through the center of the circle, and it bisects one of those sides, you've basically halved the square root of 3, because that side is the square root of 3, and where the diameter cuts through the base of that side of the triangle, it cuts it at right in half, and so that on each side is half the square root of 3.
No, of what real? Okay. Let me get to something practical. Okay, fine. Those are specific examples, but of what benefit would that be to anyone, generally speaking? To know mathematics. We do our
Well, you know how
people
consider
checkbooks and things, but not much.
Like, have you heard of the concept, like, or this idea of these values, like the golden mean?
Of course, yes.
And people talk in terms of certain constants or values that have a certain aesthetic property to them, some quality that seems to be other than the mathematics, although its pure definition is mathematical, or it's more complete and absolute expressed mathematically. But there are geometric figures and drawings that they.
Yeah, well, I mean, that's the thing. You can draw a beautiful geometry and express it mathematically.
What I noticed,
it may be beautiful to a guy who likes numbers, but the curve of a spiral shell, for example, or something like that, would be much more easily appreciated by someone seeing it or hearing the kinds of subtle sounds that circulate through it.
What I noticed,
that kind of thing. So it's not always, maybe mathematical beauty is there for someone who can appreciate it in terms of, if you can, see 10 numbers flipping around and, and arranging themselves in a certain way, then you can appreciate the beauty of that. But for most people, just seeing the curve of the geometry and the form and the texture, all that can be much more easily comprehended.
It can be, but it's limited in a certain way, and that is that people who appreciate aesthetically the concept of the golden mean in architecture, in drawings, in form, and in shape, if they were to consider its mathematical meaning and were to practice sacred geometry, like actually do it, they would notice in the practicing of it that there are ratios similar, in fact, many ratios that are similar to this golden mean that are not observed or not expressed in their architecture. And I have to ask myself, like, why would that be? Why would human beings limit themselves to this one particular value, the golden mean? And I understand mathematically its meaning, but that mathematically there are many other phenomena, mathematical phenomena, that's of a similar nature.
That are of a similar nature?
Yes, that basically has the same meaning.
Okay, so
but it's expressed with different numbers, and like...
Well, okay, but the point being what? That implicit to understanding it mathematically, there is something that can be derived from a form.
What is the quality, and then what is the attribute of the golden mean that mathematically expresses it? And you will notice that that attribute can be found in other forms, in other ratios that are not expressible by that form. In other words, the same intrinsic meaning, and it has a different form to it.
Give me a specific example, a solid example of what you're talking about.
Sure.
Are you talking about, like, let's say a spiral seashell? That's sort of used as an example of the golden section. This set of triangles that rotate around and around, and they get smaller and smaller.
What I noticed was
relationship with the hypotenuse
yeah,
and base.
Like, I'm not sure. What I've noticed is, and I think this...
Well, so give us an example of that.
I think it relates back to Plato's observations of form, and when he first came up with his ideas of geometry, was that he noticed that it had a relationship to ratio.
Okay.
That it seemed to be, that it all flowed out of this concept or meaning of ratio, that you had to have these, that ratio all of a sudden came into existence when you had these two things, and they came together and they produced this ratio, this law. Like, that's what the word ratio means, law. And I'll give you an example in terms of geometry where I've noticed it in geometry. Like you can take all kinds of geometric forms, all kinds of forms, reduce them to geometry, and you can look comparatively at the different values that exist there, and there's nothing unique about a lot of them, like there is, say, with the golden mean, like where the particular form always has this particular function. Like, if you take the inverse of the golden mean, you end up with the golden mean, right? Like,
1 over 0.618 or whatever that.
Right, and divide that.
Or is it? I can't remember. Is it?
Well, if you take 1 and divide it by 0.618, you get 1.618.
Okay, get it. Yeah.
Right.
I just wanted to make sure I had that right. And so.
And if you take 1 and divide it by 1.618, you get 0.618. Like, so it's always the inverse of it. And what I noticed was that there's...
So it turns itself inside out continuously.
And what I noticed in my practice of sacred geometry was that there were, in my observation of it, was that there are many examples of this inversion process.
Okay.
I call it an inversion process because it seems like the opposite is the same as what's happened. When you look at what you see there, and this doesn't happen to everything. Like
well, it seems like it's turning itself inside out and outside in, and inside out and outside in, right?